All right, so this is our video for week 2. We're going to go over some practice problems from our textbook on the sections that we're looking at this week. So we're going to start with section 1.5 here. For these 4 problems, what we want to do is solve each inequality, graph the solution set, and write it using interval notation. So looking at question 11 here, we want to solve this guy. So we want to get x by itself and figure out which values of x will make this whole statement true. So to do this, the first thing we're going to do is add 4 to both sides. This tells us x is going to be greater than or equal to 16. This means any x value that's greater than or equal to 16, if we plug that value into this x here, that will become a true statement. So for example, if you were to plug 16 in for this x value, we'll get 12 is greater than or equal to 12, which is a true statement because 12 is equal to 12. And then for any value greater than this, so 17, 18, and so on, we'll also get a true statement here. So the next thing we want to do is graph the solution set. So we'll draw our number line here. And let's label this guy. So we're saying our solutions are going to be all x values that are greater than or equal to 16. Now, since we have this or equal to symbol here, we're going to use a bracket on our number line at the point 16 to indicate that we're including this value. And then it's all values greater than this, so everything here. And then what we'll do is just do a big arrow here to indicate that this is going to go on forever up to positive infinity. All right, and lastly, we want to write this using interval notation. So I'm just going to abbreviate that with IN. And then in interval notation, we're going to use a bracket again to include 16. And they're going all the way up to infinity. Now, as you know from the textbook and the lecture videos that Pearson provides, we're going to use a parenthesis when we're dealing with infinity because it's not an actual number. So with positive infinity or negative infinity, if we're continuing on in this direction, we're always going to use a parenthesis. The next problem we're going to look at is 27 here. We again want to solve for x. So for this one, the first thing we're going to do is get rid of this fraction. We can do so by multiplying by -4 on both sides of our inequality. We can do this because we have a -4 on the numerator and in the denominator, so these guys are going to cancel, and we end up with something nicer on the left-hand side of our inequality, just 2x minus 5. Now, as we know, if we're going to multiply or divide by a negative number when dealing with these inequalities, what we have to do is then flip this sign here. So, this becomes 2x minus 5 is going to be less than this multiplication of 5 and -4, so -20. So we always have to flip that sign here in order for this to still be a true statement. All right. Now this becomes pretty simple. We're just going to solve for x. First, we'll add by 5 on both sides. Get this here. And lastly, we can divide by 2 to get x completely by itself. Now we can plug this into our calculator just to get a better idea of what that number is, 15 over 2, so that'll be -7.5. Now we're going to want to graph this guy, so again we'll use our number line here. We'll label this here. All right, and so our solution is going to be our solution set is going to consist of all numbers that are going to be less than -7.5 here. And we have a less than symbol, so we're going to be using a parenthesis. We're not actually going to be including this value. So graphing this here, we're going to look at -7.5, put a parenthesis there, and then it's going to be all values that are less than that. So we're moving in this direction here. And then we'll use a big arrow there to indicate that it's all values less than this number, so it's going to continue on forever in the negative direction. So then in interval notation, we're going to use a parenthesis. We're going from -infinity all the way up to -7.5, and we're not including either of those. All right, let's move on to question 38 here. Now in this case, we're going to want to use our distributive property. We have this -2 is being multiplied by what's inside the parentheses here. And since x and 4 are not like terms, we can't combine these guys. We can't do what's in the parentheses first and then multiply by -2. So we're going to distribute this -2 to both terms inside our parentheses. This will give us minus 2x minus 8. And then on the right hand side, we still have 6x plus 16 here. All right, now we're just going to want to combine like terms. We have a minus 2x and a 6x, but these guys are on opposite sides of our inequality, so we're going to want to combine them. Similarly, we have a minus 8 and a positive 16 here. These guys are also like terms, but they're on opposite sides of our inequality, so we're going to have to move them around. So the first thing we'll do is we'll add 2x to both sides of our inequality here. This leaves us with a minus 8 on the left-hand side, and then we get 6x plus 2x. That gives us 8x's. And we still have this plus 16 here. So we just moved this 2x term here on this side by canceling these guys out so that we could combine these like terms. So we're going to want to do the same thing with this 16 here. We'll subtract 16 on both sides. This cancels on this side. And then on the left-hand side here, we have minus 8 minus 16. So this gives us a negative 24 on the left-hand side. And then we still have 8x on the right-hand side. Now lastly, we're just going to divide by 8 to get x completely alone. And so this tells us x. Actually, let's keep this consistent. On the left-hand side, we have negative 24 divided by 8, so that'll be negative 3. And that'll be less than or equal to x. We could also write this as x is greater than or equal to negative 3. Either one is okay. All right, so we're going to want to graph this. Sorry, I'm running out of room. So this tells us the x values that will make this statement true are all x values that are greater than or equal to negative 3. So we have our number line here. Let's label this. All right, so these are all x values greater than or equal to negative 3. So we're going to use a bracket to include that number, negative 3, and then all the way up to infinity here. So in interval notation, we'll use a bracket, and we're going all the way up to infinity. All right, let's look at this last inequality here. Now this is a 3-part inequality. So these guys are special because whatever we do to one part of the inequality, we have to do to the other 2 as well. Similar to these 3 examples here, whatever we did to one side of our inequality, we had to do to the other. So same idea, we just are dealing with 3 parts now. So we still want to solve for x, and what's happening to x here is it's being multiplied by 2 and then we're adding 4. So we're going to undo those operations to get x by itself. I'll subtract 4 first, so these guys cancel, and whatever I do to one part, I have to do to the other 2 parts. So I'll get minus 10 here. We still have 2x in the middle, and then on the right-hand side, we're going to have 12. Now lastly, we just want to get x completely alone, so I'll divide by 2 to all 3 parts here. So I'll have negative 5 on the left-hand side and 6 on the right. So x is going to be in between negative 5 and 6. Graphing this, we'll use our number line here. And so we have negative 5, and there's a lot of numbers in between these guys, so I'm just going to plot these 2 points. That's fine. All right, so our solutions are going to be all numbers in between negative 5 and 6, and including these guys. So if we plugged in negative 5 or 6, the statement would also be true, so we're going to include them and use brackets here. And our solutions are going to be all numbers in between those 2. All right. And then an interval notation here. It's going to be all numbers between negative 5 and 6, and including these 2, so that'll look like this here. All right, so next we're going to look at some problems from section 1.6. Here we're looking at the intersection and union of sets and compound inequalities. So for this example here, we're going to let A be the set that contains these elements here, and then B be the set that contains these guys. So for question 5 here, what we want to do is we want to find the intersection of these sets. So when we're looking at the intersection, we're looking at only the elements that these guys have in common. So notice B and A both have 1 in common, they both have 3 in common, and they both have 5 in common. So the union of these two sets then would just be 1, 3, and 5. Since B does not contain 2, 4, or 6, we are not including that in the intersection. It needs to be the elements that they share. However, if we're looking at the union of these two sets, that's not the case. When we're looking at the union, we're actually just going to combine everything that is in this set and everything that is in this set. So doing so, for A, we have these elements here. And then for B, we have 1, 3, and 5, which is already contained in our set A here. So we're actually not going to write them again. We're not going to write repeated elements. We're just combining them, and if they share these guys, if they have any in common, we will only write them once here. All right, so this brings us to our compound inequalities. So what we want to do for these problems here is we want to solve each one. Again, graph the solution set and write it using interval notation. So for this one, for question 24 here, we already have that x is by itself for this compound inequality, so we don't have to do any manipulation to solve for the variable. So what we're told is that our solution set is going to be all x values that are less than or equal to -1 and all x values that are greater than or equal to 3. Now when we have this and here, we can think of and as the same as our intersection. So our final solution set are going to be the numbers that make this true here, the numbers that are going to be less than or equal to -1 and greater than or equal to 3. So let's graph this on the number line here. And what we'll do is we'll graph these guys separately. So let's do some color coding here. We'll do blue for this one, and we'll do green for this one here. All right, so let's do some labeling. So notice for this one in blue here, we're looking at all x values that are less than or equal to -1. So we're including the value of -1 here. So we'll do a bracket, and it's going to be all values that are less than that. So we're continuing on in that direction. Now for the other one here, it's all x values that are greater than or equal to 3. So we're including this value 3, and it's going to continue on in this direction. Now remember, this and here is the same as our intersection. So we want to figure out which values these guys have in common. Now notice, looking at this graph here, they don't share any values. They don't have any in common. We're looking at all values that are less than or equal to -1 and the values that are greater than or equal to 3. And there are no values that follow this here. So in this case, our solution set is just going to be the empty set. There are no numbers that are both less than or equal to -1 and greater than or equal to 3. And we can easily see that with this graph here. All right, let's move on to 27 here. Now in this case, we do have to solve this compound inequality. We want to get x completely alone. So we'll divide by -3 on both sides of this first one here. This gives us x by itself on the right hand side, and remember, since we divided by a -3, we have to then flip our inequality symbol. So we'll get -1 here. For the next one, we'll subtract 3 on both sides. So we'll get x is going to be greater than -3. And don't forget, we're looking at our and here. Okay. So let's graph both of these guys. We'll graph them on the same number line like we did for the last example. So alright. So we're looking at x values that are less than -1, but not including -1, so we're just going to do a parenthesis there. And let's stick with this color coding. Alright. So all values that are less than, but not including -1, are going to be these values here, and that continues on to infinity. Then we're looking at values that are greater than -3, so in green here. We're not including -3, however, so we're going to put a parenthesis there, and it's going to be all values and continuing on in that direction. So since we're looking at and in this compound inequality, we're looking at the intersection of these two inequalities here. And as we can see, that will be this region here. This region, we share these values from -3 to 1. And so I'll graph it nicer on this number line here. Our solution set are going to be all the numbers in between -3 and 1 here. So everything in this region. And then in interval notation, we're going to have parentheses for both of these numbers because we're not including it, from -3 to 1. So again, just to emphasize, since we're looking at and, we're looking at the intersection. We're looking at all numbers that are less than -1 and that are also greater than 3, -3. All right, let's move on to 41 here. We're going to solve our inequalities. So I'll subtract 2 from both sides on this one here. I'm going to get that x is going to be greater than 5. Now in this case, we have our or. So we're saying that x values need to be greater than 5, or, and we'll solve this one. The first thing I'll do is I'm actually going to add x to both sides in this case because we always want x to be positive. So I'm left with 1 is going to be greater than 6 plus x, and then what I can do is just subtract 6 from both sides here. So this tells me -5 is going to be greater than x. So we're looking at all values of x that are greater than 5 or less than -5. Sorry. So this or here can be thought of as this same as this union. Our solutions can be either here or there or both. So if we were to graph this on our number line here, there's a lot of numbers in between -5 and 5, so I'm just going to plot them like that there. So for this first one here, we're looking at values that are greater than 5. And for the second, less than -5. So here, it's going to be all values from 5 up to infinity. And for this guy, it'll be all values less than -5 up to -infinity. And we're not including the 5 and -5 here since we just have a greater than or a less than symbol here. All right, now since this or can be thought of as our union here, it's going to be all elements. We're going to include all of them. It doesn't have to be the ones that they have in common. So the solution to this compound inequality is going to be all these numbers here and all these numbers here. We're including those guys. So in interval notation, it's going to be all values from -infinity up to -5, and then we're going to use our union symbol here, values from 5 up to infinity. So if we were to plug in any values in this interval, so -6, -7, and so on, into this compound inequality, it will be true. And similarly, if we were to plug in any values in this interval into our compound inequality, it would also be true. So 5, 7, or 6, 7, and so on. But anything in between these guys would not be a solution. And that is just because we're looking at an or statement here. If we're looking at an and statement, then as we can see from this example 24 here, there is no numbers that these guys have in common, so that's why we got no solution. All right, now lastly, let's do 46 here. Now we have a little bit more work to do to solve for x. We'll subtract 2 on both sides. For this first one, we'll get 3x is going to be greater than or equal to -9. Then we'll divide by 3 on both sides. So we're just going to get that x is going to be less than or equal to -3. We're dealing with our or statement again. So to get x by itself, I'll subtract 1 first. Let's stick with the same colors. I'll get -2 is going to be less than or equal to 8 here. Sorry, that's -2x on the left-hand side is going to be less than or equal to 8. And then to get x completely alone, we're going to divide both sides by -2. So x is going to be less than or equal to -4 here. Oh, and actually, if you caught my mistake here, remember whenever we multiply or divide by a negative number, we have to flip our inequality. So we got to be careful with that because we divided by a negative. So this is going to be greater than or equal to -4. All right, so let's graph this on our number line here. Stick with our color coding, and then let's label this. All right, so our solutions are going to be numbers that are any less than or equal to -3. So we're going to use a bracket for this one. All numbers less than that is going to continue on in this direction to -infinity. Now on the other hand here, we're looking at all x values that are greater than or equal to -4. And we're going to use a bracket. -4 is here, and all values greater than that, so that'll continue on to +infinity. Now in this case, if we were looking at an AND statement, we'd look at the numbers that they have in common. So that would just be this little interval here, but we're looking at the union. So we're taking all of these solutions here. So in this case, for interval notation, this would just be all real numbers. If we look at this one, it's going to be all values less than or equal to -3. So all of these values up to -infinity here is going to be a solution. And on the other hand, we're also looking at solutions that are going to be greater than or equal to -4. So looking at this number line here, this is going to be all real numbers. And then in interval notation, that'll be -infinity to +infinity. All right, so now we're going to do some problems from section 1.7. We're looking at equations or inequalities with our absolute value symbols here. So this here is just a screenshot from our textbook, and it involves the 3 cases when we're solving absolute value equations and inequalities. So the first case here, if we have something of this form, in order to solve this compound equation, we're going to rewrite it like this guy here. So whatever is inside of our absolute value is going to be equal to this number here, or we could have that whatever is inside this absolute value is going to be equal to -k. Now you can watch the Pearson lecture videos or go into the textbook to kind of get a better idea of why we have these 3 cases here, but essentially it's because of our absolute value signs. Right, if we plug in a positive number here, we're going to get a positive number outputted for our absolute value. And if we were to plug in a negative number here, we would get a negative number, or we would get a positive number outputted. So essentially we have a positive or negative solution here. So that's why we translate this into whatever's inside our absolute value. It can be equal to +k or -k. Now our solution set is usually going to be of this form here, which just includes 2 numbers. And so what we can do to graph that is just plot these numbers on the number line. Now in our second case here, we have the case where our absolute value is going to be greater than some number k. So we end up with this compound inequality here, where what's inside our absolute value can be greater than k, or what's inside this guy can be less than our -k value. So this, our solution set looks like this in interval notation and looks like this on our number line. And then lastly, our third case, if we have this case here where our absolute value is going to be less than some number k, then we end up with our 3-part inequality. And our solution set is usually of this form here. It just consists of a single interval. Now something to keep in mind here is that for all 3 of these cases, it translates to an OR statement. So we're thinking of it in terms of a union, which is what we saw in section 1.6 here when we were looking at the union of our sets and our compound inequalities. All right, so let's look at this first example here. For question 11, we have the absolute value of 2x minus 1 is going to be equal to 11. And going back to our cases here, this is going to be the first case. So we're going to rewrite this and solve this compound inequality. So we have 2x minus 1 is equal to 11, or 2x minus 1 is equal to -11. So we just want to solve for x in both of these cases. Doing so, for this first one here, we'll just get x is going to be equal to 6. Or, doing the same thing here, we'll get that x is going to be equal to -5. So we can plot that on our number line. We know it's just going to look like our number line and then our 2 points here, so -5 and 6. So these are our solutions, and so our solution set is just going to consist of these two numbers, so -5 and 6. All right, so that was the first case. Now for this next question here, this is going to be our second case. We have our absolute value is going to be greater than some number k. So in this case, we're going to have to translate it to that compound inequality. So we'll get that 5x plus 2 is going to be greater than 10, or 5x plus 2 is going to be less than -10. So from here, we just want to solve for x. So for this first one here, we'll get x is going to be greater than 8/5. And then plugging this into our calculator, this will be 1.6. Or doing the same thing on this side here, just solving for x. So we'll divide by 5 again, and we're going to get x as less than -12/5. And then plugging that into our calculator, we'll get -0.8. All right, so let's graph this on our number line here. And we kind of have an idea of what this solution is going to look like because of the fact that this is our case 2. But here, let's plot some numbers. All right, so we know that a solution is going to be all x values that are greater than 1.6, but not including that number. So we're going to use our parenthesis. So that'll be right about here, and all numbers greater than that guy. And on this hand here, it's going to be all numbers that are less than -0.8. So that'll be right about here. We're not including that one. So all numbers less than that. And since this is a union, it's going to include all of these and all of these guys. And then we know that in interval notation, that's going to be -infinity up to, and I'll just write this using our fractions here, up to -12/5 or -0.8. Then excluding everything in between that. None of these guys are solutions. And then picking back up at 8/5 or 1.6, all the way up to infinity. Now lastly, this is going to be our last case, case 3. We have the absolute value is going to be less than or equal to some number. And although we don't have the or equal to sign here, we're still dealing with that in this case. As we can see that here, this will also apply to these inequalities as well. This just includes our endpoints. All right, so we're going to have the 3-part inequality in this case. So we have that what's inside our absolute value is going to be in between -3 and +3. And so we just want to get x by itself. So I'm going to subtract 5 from all 3 parts here. Remember, whatever we do to one part in this 3-part inequality, we have to do to the other 2. So on the left-hand side, I'm going to get -8. And then we have this -x in the middle. So we're going to address that in a moment because we do want x to be completely alone. If we have a negative in front of our x, it's not by itself. So what we'll do here is we'll just divide by a -1. When we're dividing by 1, we're not actually changing the value of this inequality. And then, And then the fact that we're dividing by a negative is going to change the sign of our x so we can get it completely by itself. But we do have to remember, since we're dividing by a negative, we're going to have to flip these inequality symbols here. So what I mean is, on the left-hand side, we have -8 divided by -1. That gives us a +8. But we have to flip that inequality symbol. We get a positive x in the middle. And similarly, we're flipping this inequality symbol, and we get a +2 on the right-hand side. Now we can rewrite this. We're usually more comfortable with writing this with our smallest number on the left-hand side. We like to read from left to right, so that's how we'll write our inequalities as well. So we can just rewrite this by flipping the symbols and our numbers here. So x is going to be some number in between and including these endpoints 2 and 8 here. So we know how to graph that using our number line here. If that's 2 and that's 8, it's going to be everything in between these guys, but also including them. So we're going to use our brackets, and then our solutions are going to be everything in between. And then in interval notation, we use our brackets again. All our solutions are going to be from 2 to 8. All right. Now the next several examples, we're going to look at some special cases. In this first example here, we are dealing with an absolute value inequality, but we have to rewrite this so it's of the form that we're familiar with. If you go back to this guy here, all of these cases just have the absolute value by itself. So what we're going to have to do is just rewrite this guy. And we'll do that just by moving this 3 to the other side of our inequality. We'll end up with 2x plus 1 is going to be greater than 5. And so now we're more comfortable with this form here. We have our absolute value by itself, and then we have that this guy is going to be greater than 5. So in this case, we're dealing with case 2 here. So we're going to write this compound inequality and then solve for x. So we're going to end up with 2x plus 1 is greater than 5, or 2x plus 1 is less than negative 5. So what we can do here is just subtract 1 on both sides of our inequalities for both of these. We'll end up with 2x is going to be greater than 4 on this one, or 2x is going to be less than negative 6 for this guy. I'm running out of room, so let's put this up here. Now all we want to do is divide by 2 for both of these inequalities to get x alone. So we'll end up with x is going to be greater than 2, or x is going to be less than negative 3. Now we'll plot this guy on our number line here. Nope. So we have negative 3 here and 2 here. So our solution is going to be all x values that are less than negative 3, but not including that guy. So we're going to put a parenthesis here. And our solutions are going to go to negative infinity. Then we also have solutions that are going to be greater than 2, but not including that guy. So we're going to put a parenthesis here. And our solutions are going to be all numbers greater than that, so going to positive infinity. And then in interval notation, this is going to be from negative infinity up to 3. Those are all of our solutions here. And then union from 2 to infinity. All of these guys here, and then not including everything in between. All right, let's look at another example. Now this one here, we have an absolute values equal to an absolute value here. But this is still an example of case 1 here. We have an absolute value is going to be equal to something. Now in this case, our k is just another absolute value expression. So all we're going to do here is rewrite our absolute value equation as a compound equation in this form here, but instead of just k and negative k, we're going to have what's inside of our absolute value expression. So what I mean is, we know what's inside of our absolute value on the left-hand side is going to be 3x plus 1, and it's just going to be equal to positive k. Now in this case, k is just going to be 2x plus 4. All right, now on the other hand, we have that our left-hand side is going to be equal to minus k. So if k is this whole thing, 2x plus 4, then it's going to be minus this whole thing, 2x plus 4. So we have to put this in parentheses because we have 2 terms here. So this minus needs to be distributed to both terms inside our parentheses. All right, so we want to solve for x. So first, let's solve for x with this guy here. Oh, this guy here will be a little bit easier to do so. So we're just going to combine like terms. We have a 3x and a 2x, so we want to get these guys on the same side, and then a 4 and a 1. These are also like terms, so we want to get them on the same side. So I'm just going to do that in one step here. I'm going to subtract 2x on both sides of our equation, and in the same step, I'm also going to subtract 1 on both sides. Right? If that's too confusing, you don't have to do that in one step. You can do it separately. But I'm just going to do that to save room. So we have 3x here minus 2x, so that'll just leave us with 1x here. And then we moved this 1 to the side. So we have 4 minus 1 here. That just gives us a 3. Okay, so that's one of our solutions. Or we're going to solve this guy here. Now we're going to do something similar, but the first step we have to do is distribute this negative to both terms inside our parentheses here. This gives us minus 2x minus 4, and then we can solve for x, doing something similar. We will add 2x to both sides and take away 1 in the same step. So now we have 3x plus 2x. That'll give us 5x's. And then we got rid of this 1 here by subtracting 1. These guys cancel, so what's left on this side is minus 4 minus 1, which gives us a minus 5. So then we'll just solve for x by dividing by 5 on both sides. So this tells us x is going to be equal to minus 1. So our solution then, plotting it on our number line here, is going to be minus 1 and 3. So these points here. And then our solution set is going to be minus 1 and 3 written this way. Right, now the last thing we're going to look at, this last special case here, is this problem. So again, we want to rewrite this absolute value inequality here because we want the absolute value by itself on this left-hand side. So we're just going to add 2 to both sides of this inequality. We're going to get the absolute value of 4x plus 1 is then going to be less than negative 3. Now, before we look at what kind of case this is and try to solve, the first thing we'll notice is that we have an absolute value by itself on this left-hand side. And remember, no matter what, when we're taking the absolute value of a number, whether it's positive or negative, we're always going to get a positive value outputted. So this here, the absolute value of something, can never be less than 0. It'll be 0 and up. But here, this is telling us that this whole absolute value is going to be less than negative 3. Any number less than negative 3 is negative, but we know, we just said an absolute value can't be negative. So we'll write that here. Our absolute value is never negative. So in this case, our solution set is just going to be the empty set. So there is no solution for this guy. Now, this brings us to section 2.1 here. So we're looking at graphing. So we just have a couple problems here. Now this first example, what we want to do is we want to complete this table here and then graph this equation by plotting each of these points. So we have this equation here. Now we're looking at linear equations in 2 variables. So we have x and y. Now, if we want to complete this table, we see values plugged in for x and y. And so what we want to do is plug in these values and solve for the other variable. So the first case here, we're told that x is equal to 0. So we want to figure out what y is equal to if x is equal to 0. So we're just going to plug 0 in for x, and I'll put it in parentheses to emphasize that we're plugging it in. So we'll add 3, let's rewrite that. We'll add 3y, go. That's equal to negative 5. Now what we want to do is just solve for y. We have 0 plus 3y, so that just gives us 3y on the left-hand side. So we'll divide by 3 on both sides here. So y is going to be equal to minus 5/3. So that is what this point is here in our table. When x is 0, we get y is equal to negative 5/3. Now let's do the same thing, but in this case, y is now equal to 0, and so we want to solve for x when y is equal to 0. So we have x here, and we're going to plug in 0 for y into this equation. Doing so, this actually goes away. 3 times 0 is going to give us 0, so we just have x on the left-hand side, and then on the right-hand side we have negative 5. So pretty simple for that one. X is just equal to negative 5. Now let's do the same for the last two here. This one we have x is equal to 1, so we'll plug in a 1 for x, and then we want to solve for y. So I'll subtract 1 on both sides. we're going to get 3y is equal to negative 6, and then just dividing by 3 on both sides, we'll get y is equal to negative 2. So we'll plug that into our table here. And then lastly, we want to figure out what x is going to be equal to when y is negative 1. So we're going to plug negative 1 into our equation. This gives us x minus 3 is equal to negative 5. And so we're just going to add 3 to both sides here. So this gives us x is going to be equal to negative 2 as well. All right, so we can just, what we'll do is plot these points here that are on this table and then connect them and graph our equation. So the first point here is 0, negative 5/3. So I'll put that in coordinate notation here for each of these guys. All right. For each of these points, right? Because we're looking at x and y coordinates. So when x is 0, y is negative 5/3. When x is negative 5, y is 0, and so on. So that's how we're going to plot these points. When x is equal to 0 here, y is negative 5/3. So x is 0, so we're not moving anywhere on our x-axis, but y is negative 5/3, so we're moving down 5/3. So that'll be right about there. That'll be that point. Now our next point is negative 5, 0. So that means x is going to be negative 5, so we're moving to the left, negative 5 for x. And then that is our point because y is 0, so we're not moving up or down on our y-axis. Now our next point is 1, 2, or 1, negative 2, so that'll be that point there. And then lastly, we have negative 2, negative 1. So our line is going to look something like this here. Oh, trying to make it straight. All right, so that is a rough sketch of our line for this equation here. Now we're going to do something similar for this example here. What we want to do is find the x and y intercepts and use that to graph this equation. So if you notice, for this last example, this point here is where our graph intersects the y-axis, and then this point here is where it intersects the x-axis. So this is our x and y intercepts respectively. If you go back to how we found those points, we actually can find them by plugging in our value. So if we wanted to find our y-intercept, for example, we would set x equal to 0 and solve for y. And if we wanted to find our x-intercept, we'd set y equals 0 and solve for x. So that's exactly what we're going to do for this example here. I'll show my work down here. So if we want to find our x-intercept, we set y equal to 0. So plugging that into our equation's up here, 2x plus 3y is equal to 12. So I'm setting y equal to 0 and then solving for x. I'll get 2x is equal to 12, and then I'll just divide by 2 to get x by itself. So x is equal to 6. So this means our y-intercept is going to be 6, 0. Or sorry, our x-intercept is going to be 6, 0. Now for our y-intercept, we're going to do the same thing, but now setting x equal to 0. So we have 2 times 0 plus 3y is equal to 12. Okay, so just plugging x is equal to 0 into our equation up here. All right, so this gives me 3y is equal to 12, and then we'll divide by 3 on both sides. So y is going to be 4. So this means our y-intercept is going to be 0, 4. Okay. We plugged in x is equal to 0, and we got y is 4. Now, when we are plotting equations, we really only need 2 points to do so. Or I mean, when we are graphing an equation, we really only need 2 points to plot. What we could do to graph this, guys, we could plug in another point or create a table like we did in this last example to get a more accurate line. But in this case, we're just going to plot these 2 points, the x and y intercept. So we'll plot 6, 0. So x will be 6 and y will be 0, so that'll be this point here. And then for our y-intercept, we have x is 0 and y is 4, so that'll be this point here. Okay, so our y-intercept is where our graph's going to intersect the y-axis, and our x-intercept is where our graph's going to intersect the x-axis. So connecting these 2 points, we get a rough sketch of our graph here. Let me do that a little better. So that is our graph for this equation. Now the last 2 examples we're going to look at. First, we want to identify which of the following equations has a graph that is a horizontal or vertical line. So first, for A here, what we're going to do is get x by itself, because we're going to end up with x is equal to 6. Now in this case, this is going to be a vertical line, because going back, we're going to use this graph here. So if x is equal to 6, that's this point here, and our line is just going to look like this going through that point. So we just have a vertical line, x is 6, that'll be our solution there. Now, on the other hand, if we have y is equal to some number, so here y is equal to negative 10, we're looking at our y-axis. So we have negative 10 here, so we're going to have a horizontal line like this. So this guy is horizontal. And then lastly, we have x plus 1 is equal to 5, so we're going to subtract 1 on both sides to get x by itself. So we have that x is equal to 4, that's our solution, and that's the same form as this guy here. So our solution is just going to be this guy here, so we have a vertical line. Alright, and then the very last thing we're going to look at is this example here. We want to find the midpoint of the line segment with these, we want to find the midpoint of the line segment with these endpoints here. So what we mean is we just have a line, and these are the 2 endpoints, and the line is connecting them. So we have a formula for this, our midpoint formula. We're going to end up with coordinates. So our midpoint formula says x1 plus x2 over 2 is our first point, and then y1 plus y2 over 2 is our second point, our y coordinate. Now going back to these points here, or I guess in this midpoint formula, these are arbitrary. So this just represents any x1, x2, y1, and y2 coordinates. So going back to these endpoints here, we can label these. This is our first x coordinate, so we'll just label that as x1. And this is our second y coordinate. This is our first y coordinate, so we'll label that as y1. Now for the next pair, we have our second coordinate, so we can label this as x2 and y2. And it doesn't really matter, you could also label this as x2 and y2 if you wanted, and this one is x1 and y1 if you wanted, but whatever you choose, you have to plug it in correctly into this formula here. Okay, so don't get too caught up with this notation here. This is just to represent that we're dealing with 2 different coordinates here and labeling them accordingly so we can plug them into our midpoint. Alright, so plugging them in, I have x1 is going to be 5, x2 is going to be negative 1, and that'll be over 2, and then y1 is 2, and y2 is 8, and that'll be over 2. So this gives us, we have 5 minus 1, so that'll be 4 over 2, and then we have 10 over 2. So our midpoint coordinate then is going to be, is going to be 2, 5. Okay? So if we're looking at a line here, let's say this point is negative 1, 8, and this point here is 5, 2. Then exactly between these points, so the midpoint would be this point, 2, 5 here. Alright, so that'll be it for this video.